This topic is to know the procedure used to perform a tensile test and to understand the test results.
The tension test is used to determine the behavior of a material as it is pulled gradually to its breaking point. This is perhaps one of the most valuable destructive tests because it provides data on the strength, ductility, and soundness of weld and base metals, all of which are of primary concern to design engineering.
There are a variety of tensile tests, differing primarily in the specimen's shape and location of removal. All weld metal and all base metal specimens are used to determine the strength and ductility properties of each. These tests are commonly used to classify base and weld metals to national standards. For instance, filler metals must meet minimum mechanical properties as specified by the American Welding Society's Filler Metal Classification System.
All base metal specimens may be removed either longitudinally or transverse to the rolled direction of the plate. All weld metal specimens are machined from the center portion of a test coupon. It must consist entirely of weld metal in the reduced section in order to ensure evaluation of weld metal only. The ends of the specimen are shaped to fit the jaws of the testing equipment being used. Published codes provide requirements regarding preparation of the specimens which must be considered. The reduced section of the specimen is usually tapered about 5/1000 inch from the ends to the center. This allows the fracture to occur approximately in the center, where the specimen is thinnest. The diameter at the center will vary depending on material thickness and code requirements. They are sometimes used as names to describe the tensile. For example, an inspector may call for a 505. The finished surface should be smooth enough to prevent premature failure. A rough surface could cause a fracture in an undesirable location.
When evaluating all weld or all base metal specimens, it is essential that the applicable specification be reviewed to determine exact testing procedures. For the next few moments, we'll step through the procedures used to test a 505,000th inch specimen.
The 505 specimen is marked with a center punch at 2 points 2 inches apart. This is known as gauge length. The original gauge length of 2 inches is recorded for use later in calculating ductility. The specimen is then secured in the jaws of the tension machine. An extensiometer, a type of strain gauge, is attached to the specimen to detect changes in length when force is applied. The equipment operator begins the pulling process by allowing the machine to apply pounds of force, or load, to the specimen.
As force is applied, stress develops. This stress is equal to the force applied, divided by the cross-sectional area of the specimen. The area of a 505 specimen is determined by squaring the diameter and then multiplying by pi, or 3.14. This value is then divided by 4. By substituting the numerical values, the result is 2/10 square inch. If the force is equal to 5,000 pounds, the stress becomes 25,000 pounds per square inch.
As force is applied, the specimen begins to stretch or elongate. This is commonly referred to as strain. The units for measuring strain are inch per inch, which is the amount of increase in length per inch of gauge length. The tensile equipment is designed to plot the stress in relation to the strain. The slope of this line is the metal's modulus of elasticity. The gauge attached to the specimen detects the elongation, which is then used by the equipment to plot the strain. The resulting curve is called a stress-strain curve. Notice that in the lower part of the curve, the stress is directly proportional to the strain.
Under these loading conditions, the material is in an elastic state. This means that if the load is removed, the material will return to its original length. As the load continues to increase, the material eventually reaches its elastic limit at point A. Here the material begins to yield. When the material yields, it will permanently elongate, sometimes referred to as plastic deformation. Under these conditions, the material is in a plastic state, which means that if the load is removed, the material will not return to its original length.
The point at which the material is permanently elongated is called the yield point. This is defined as the load that causes a marked increase in strain without increase in stress. In many cases, the yield point is difficult to determine. A decrease in stress may be detected and is shown as a knee on the curve. Because of this, yield strength is more commonly used to describe the point of yielding or permanent deformation. The yield strength is determined by drawing a straight line parallel to the straight portion of the curve. This is described as an offset method, since the distance between the lines is a percentage of the original gauge length. For example, a 0.2% offset indicates that the distance between the lines is the 2-inch gauge length times 2 thousandths, which equals a distance of 4 thousandths inch. The point at which the offset line crosses the original curve is the yield strength. If the intersection occurred at a load of 8,000 pounds, we can divide the load by the cross-sectional area to determine the yield strength. In this case, it is 40,000 pounds per square inch.
After the material has yielded, the strain gauge is usually removed to prevent damage to the gauge when the material fractures. As additional load is applied, it reaches a maximum value at point B called the ultimate tensile strength. Here, a noticeable reduction in area and increase in length will occur as the load increases. By dividing the maximum load by the original cross-sectional area, the ultimate tensile strength can be calculated. In this example, the maximum load is 16,000 pounds. By dividing the load by the cross-sectional area, we find that the ultimate tensile strength is 80,000 pounds per square inch. From the results of the test, we now know that the yield strength of the material is 40,000 pounds per square inch, and the ultimate tensile strength is 80,000 pounds per square inch.
Once the ultimate strength is achieved, the actual stress may decrease as the material fails. This is due to the significant reduction of area which occurs in later stages of the test.
The broken specimen is used to calculate ductility through percent elongation and percent reduction of area. The percent of elongation is determined by measuring the final length between the punch marks with calipers or a micrometer. The difference between the original and final lengths is divided by the original length and then multiplied by 100 to obtain the percentage. In our example, the percent of elongation is 20%. A higher percentage indicates a greater ductility.
To calculate the reduction of area, measure the smallest cross-section of the fractured specimen. The difference between the original and final area is divided by the original area, then multiplied by 100. In this case, the percent reduction of area is 43.5%. Again, a higher percentage indicates greater ductility.
The all-weld metal tensile test is most commonly used to specify and classify welding filler metals. Another group of tensile tests include the reduced section test and the full section test. Full section tests are commonly used on small diameter pipe or tubing or thin material where it is difficult to remove specimens to qualify welding procedures.
Usually the specimens are removed from plate or pipe welds, transverse to the direction of welding. The type, size, and number of specimens will depend on code requirements. Once the specimens are removed, they are machined to the required dimensions. The term reduced section is used since the middle of the specimen is thinner than the ends. The reduced section is placed on the tension machine and pulled to failure. The strain gauge is normally not used to perform these tests.
Most codes require that the ultimate tensile strength be equal to or greater than the minimum of the specified tensile range of the base metal welded. For example, if the minimum published tensile strength is 58,000 pounds per square inch, then the ultimate tensile strength recorded from the test must be at least 58,000 psi.
It is important to review the applicable specification to determine the proper procedure and type of coupon based on the qualification to be performed. The tensile test is extremely valuable for determining weld soundness and mechanical properties. It is most often used to verify material properties and to qualify procedures, and can also be used on random samplings of production parts.